from the tank at a rate, R of t. And the R of t is up here. Okay, so you have both of them are rates. That's a very important keyword for both, okay? Where R is differentiable, okay, that's good to know, and decreasing, okay. Selected values, oh, there's that fun word selected, okay. So there might be some hidden ones there, but it's a good thing that they're telling us they're selected, all right. At time t, ooh, maybe an initial. There are 50,000 liters of water in the tank. That's an amount. That is not a rate, that is an amount. All right, that's liters. Estimate R prime. Well, we all know prime means derivative, it means slope. So all I have to do is go to the R, which is right here, and find the slope at 2. Well, 2 would stick right between 1 and 3, so I'm going to use these values to help me calculate an approximate slope, okay? So I'm going to write the approximate slope here is going to be difference of the y's all over difference of the x's, like so, okay? And that's slope of R, right? Also, notice when it says indicate the units of measure, carefully read that. When you see that, you know that's going to be worth 1 full point, all right? So you need to make sure if it says indicate the units, you indicate them, all right? If it doesn't say to indicate it, then they're going to be very soft and loosey-goosey when it comes to grading your question. They won't care if you have the right units or not. But here they're going to care. Yes, Alex.
Excuse me, that's supposed to be a 1 out of 2.
Oh, did I not copy correctly? Oh, thank you. I think in my head I was thinking 3 minus 1 is 2. Thank you. Okay, is that good so far? Okay, so now the units. How do you analyze the units? Well, up here is difference of the y's, right? If you look, the units are liters per hour. Down in the denominator, those units are hours. So how to calculate this? You could say, well, it's liters per hour times, and I could do the reciprocal here, right? 1 over hours. And see how I'm getting liters per hour squared. So those would be the units I'm going to use. All right, so using unit analysis. All right, and so then basically you can take your calculator and type those ugly numbers in. You should have got, so here's the grading part of it, a negative 120 liters per hour squared. You get 1 point for the estimate and 1 for those units. Any questions on A? Nope, let's go to B. Okay, B says use Riemann's sum, okay, with 4 subintervals indicated by the table to estimate the total amount of water removed from the tank during the 8 hours. Removed. So this right here, our highlighted green here was the removed, and this is a rate. To get an amount, we have to antiderive the rate, okay? So what I'm going to do is take the rate, which is right here, and I'm going to antiderive it. What does that mean? That means if I antiderive from 0 to 8, because that's the time frame they want us to do, of the rate, it'd be great if I had an equation, but I don't. So thank goodness, integral means area, quote unquote, under the curve. And they said use left Riemann's sum. Okay, I will. I'm going to use left Riemann's sum. So I think it said 4 subintervals. So here's 1 interval. We'll do 2 intervals, 3 intervals, and 4. Okay. Left sides would be, this is the left, this is the left. This is the left for the blue rectangle, and this is the left for the purple rectangle. All right. And now you know how to do Riemann's sum. It's just base times height. So notice this one's not equal in terms of all the widths, is it? So the span from 0 to 1, that's only 1. So 1 times 1340 is what I'm going to write down for that first rectangle. Okay. 1 times 40. Now I'm going to come along and get the second rectangle using the left side. That's my green rectangle. The span between 1 and 3 is 2. So 2 times 1190 would be the base and the height. Okay, the third rectangle is my blue rectangle. That is a span of 3 there times 950. All right. So 3 times 950. And finally, wow, my handwriting is awful. The purple rectangle is a span of 2 times 740. So So 2 times 700. Come on now. Okay. And then did it say anything about units? Well, it says use a left Riemann sum with 4 subintervals indicated by the table to estimate the total amount of water removed during the 8 hours. Oh, second question. Is this an overestimate or an underestimate of the total? And then give a reason. Well, you know, interesting things were stated up here. Like, I think this was kind of interesting where they said R is differentiable, which means you can take the derivative, so there's no holes, no asymptotes, no cusps, no funny business, okay? And it's decreasing. So can you imagine, I'm gonna take R and just draw a fictitious R here. I'm not saying that's exactly what it looks like, but it's definitely decreasing and it's continuous, right? Because I can take the derivative everywhere. And can you imagine grabbing, let's say at 0 here, my first number would be like 1340. Can you imagine grabbing the left Riemann sum and then the next rectangle would start and go from 1 to 3 and I would grab the left Riemann sum. Do you see what's happening here? Do you see that all these rectangles are above the actual curve, which means all of my approximations here are going to be larger than the actual answer, right? The actual answer, if I could find the area, I would under this curve here from 0 to 8, but I don't know the equation. So using this approximation, my approximation is going to be larger than the actual answer. So here's how you can answer this, okay, for the points. Okay, so notice what they did here. They did exactly what I just demonstrated using, you know, one of the rectangles too. You don't have to show this line. You can go straight to that second line, okay? Because look how they're grading it. They're saying 1 point for left Riemann sum. Okay, so, and then 1 for the estimate. So let's just say you knew it was 1 times and you wrote down 1349 by accident, okay? And then 2 times, they probably would say, okay, clearly they know to grab the left-hand side. They'll give you that point, but whoops, when they did make a mistake with the actual answer, all right? So if you got the answer, more than likely you got both of the points for Riemann sum and the estimate. Overestimate with reasons, the last point here, notice how they stated this clean little thing. They said it's an overestimate since R is a decreasing function. Or you can draw a little picture like I did up here and say, you know, since the rectangles are larger than the actual curve or extended beyond the actual curve, anything like that, okay, then, you know, my estimate was an overestimate from the actual. Okay, so you don't have to use the exact verbiage that they're doing, all right? As long as you're getting your point across and you're explaining it to the AP readers so that you're proving to them you understand, you're not just guessing. You can't just say, I'm gonna guess and say it's an overestimate, hope I get the point. You have to have something to back it up, okay? Any questions on B? Okay, let's do C. Use your answer from part B to estimate the total amount of water in the tank. Okay, I want the total amount of water, okay, of H2O. All right, now, the total amount in the water at the end of 8 hours. Do you agree this tank, before things were being pumped in and pumped out, right? Before the water was being pumped in, the water was being pumped out. There was an initial 50,000 liters already in the tank. So that's where we start. We say, okay, we start with 50,000. Now to add, we're going to see. So water was coming in, water was going out. All right, so between 0 and 8, water was coming in. I think that was R or T, if I'm not, I got them mixed up, don't I? No, in was the W of T. I knew it. Okay, W of T, that was water coming in. So we're adding up all the in. This is the initial, so to speak. Okay, we're adding up all the in and we're subtracting all the out. Well, the out, they said to use our approximation from B. I already forgot what that answer was. That was 8,050. Okay, and that would give you the total amount of water. Now remember, when you have a rate and you're anti-deriving the rate, you'll get the amount. Right? It's like going from velocity, which is a rate, Anti-derive it and you get position. It's an amount. Okay, so that's what's happening here. Now the rest you do on your calculator. Don't do any more work. All right. So what we're going to do is I'm going to go right to the calculator. I've already typed in the 2000 e to the negative. I think the other one's for the second question. So Y1 has that part. Then I'm going to go to the home screen and I'm going to go 50,000 plus math. Function integrate for me is 9. I'm running it from 0 to 8. And what am I trying to anti-derive? That rate that the water's flowing in at. And I stored that in Y1, okay, with respect to X. And then, of course, we have the minus, was it 80, 50? Okay, 80, 50. So you type all that in and you get the answer. Please don't anti-derive by hand. You have the tool, use the tool. Okay, so I'm gonna show you how the points worked out on that. This is letter C. Let's see, is that what I got? 49, I forgot, let me look real quick. 49,000, yeah, I did. Okay, so how the points were allocated for this, you get 1 point for the integral. That is at least recognizing that you're going to have to anti-derive a rate to get an amount. Okay, so even if you forgot the initial and you forgot everything else, you get 1 point for at least recognizing you're gonna have to anti-derive that. And then you have to just jump right to the answer and look for that for the estimate, okay? Any questions on C? Okay. Letter D. I hope you're not chatting because I haven't been looking at the chats, folks, okay? Letter D, right here. Between the times of 0 and 8 including, right, there is a time t when the rate at which the water is pumped into the tank is the same as the rate at which the water is removed from the tank. Explain why or why not. When they do something like that, like justify or explain, 90% of the time they want you to use a theorem. Okay, you only know 6 theorems. You know the mean value theorem, Rolle's theorem, you know the first fundamental theorem of calculus, the second fundamental theorem of calculus, the squeeze theorem, and the intermediate value theorem, which is the one we're going to use here, right? So let me show you how we use that. Okay, so what they did here, all right. First of all, I probably would have noted on my paper, we want to know when WT is equal to R of T. That's probably what I would have noted first. So I wouldn't have exactly followed their protocol. And then I might have set one side equal to 0 because that's nice and fun to solve for, okay? However, I have a formula or an equation for W of T. I do not have one for R of T. That was just a chart of values. So unfortunately, I can't just type this in my calculator because that would be nice and nifty. But what I can do is the following. I can use the idea of what's called intermediate value theorem, all right, where I'm going to look at 2 things, okay? I'm going to look at W of 0 minus R of 0. That's an endpoint. That's an endpoint, okay? And I'm going to look at the other endpoint, and I want to show you why I'm doing this, okay? So when you type these into your calculator, now you can use, all right, just your home screen, the vars feature, right, to find W of 0 minus R of 0. Okay, if you don't mind, I'm going to save a little time. When you type that in, because R of 0 is coming from the chart, right? W of 0 is just vars and then 0. That should give you, let me see, I'm going to cheat a little bit. That should be a positive number, okay? Now the W of 8 minus R of 8, when you type that in, I'm going to cheat a little bit, look at the answer. You just type it in, it's not a big deal. You get a negative. Ooh, what does that mean? We went from some negative number to some, and I don't know where the negative number is, to some positive number. Do you agree, according to the intermediate value theorem, if it was continuous, which they told you it was differentiable, right? If something's differentiable, you know it's continuous. It has to be. Because differentiable means you could take the derivative at any location, which means it has to be continuous. So that means in order to pass over to get to the other one, you have to then have hit a 0. So see how they said this? Therefore, the intermediate value theorem guarantees at least one time for which that is equal to 0, right? Which we got that from that statement. You don't have to state it exactly like this, but they will give you a point for somehow talking or thinking about W of t minus R of t, okay? And they're going to give you the other point for some kind of an explanation. In this case, they probably wanted the theorem in there somewhere, okay? All right, now, let's look. Oh, any questions? Sorry. Okay, let's look and see how the scoring statistics work for this. So for question 1, as you can see, the average was about a 4 back in the year 2016. Out of 9 points, and the average was a 4. So you can you don't have to share with me. You can just kind of treat that as your own information, okay? On the AP website, they actually had these scoring statistics. So if you ever want to kind of compare and contrast how you're doing with the population of folks that are taking this exam, all right, it's there for you. All right, I'm going to move on to the second question so we don't miss a beat here. Oops, hang on, my computer's stuck, so I'm going to have to go here and then back to here. And that allows me to move it. Okay. All right, here's free response number 2. So what do we know? Well, for times greater than 0, we have a particle moving along the x-axis. The velocity, this is the velocity, right? That's a rate, okay? The particle is at a position. Ooh, now that's not a rate, that's a position when time is 4, okay? At time 4, is the particle speeding up or slowing down? Oh my heavens, do you remember a long time ago, we did the running little man. He had a little suit on, he moved back and forth on the computer for us. But also I think I demonstrated with an eraser where I threw the eraser up and I said, okay, when it comes down, the velocity is negative, acceleration is always negative. You see how it's speeding up? So what does this all mean? If the signs of acceleration and velocity, if they are the same, their forces, or those forces are working together and it's going to speed the object up. If they're working against each other, the signs are different, then it's going to be slowing it down. So all you have to do, all right, now watch this, right? I have in my y2, it's sitting right there. That's my velocity. All right, I kind of pre-did this before we had this. I'm going to go to VARS and I'm going to let the calculator, right? It's in y2. Do you see how quick this is? I'm going to let the calculator calculate it at 4, I think was the value. That's a positive number. I don't have to write down the exact number. I can just go here and say it's positive. Now for the acceleration, let the calculator do the work. Do not waste valuable math minutes. Here's what you do. You go, okay, I want to use math and I want to let the calculator take the derivative. That's number 8. With respect to x, I want the calculator to take the derivative of what is in y2 for me, but at a very particular location. I want the derivative at 4 because the derivative of velocity is acceleration, all right? There, it did it for me. It's a negative. So then I come over here and go like this. You can also, if you want, specify that you understand that's the case, okay? All right, so what does this mean? Well, the signs are different, so it should be slowing down. Let me show you how the points worked out on this. It's 2 points. They didn't quite say exactly how they allocated the 2, but you've got the work demonstrated here that you know to look at velocity and acceleration. That's impressive. And then a concluding statement saying it's slowing down. And don't just say you're guessing that it's slowing down. You're not going to get the point for that. You've got to back it up. You've got to prove to the AP readers you know your stuff. Okay. So you have to say it's slowing down since the velocity and acceleration have different signs. There you go. It's been proved now. You're good. Okay. Any questions on A? Getting wrinkled foreheads. Any questions? No? Oh, okay. Okay. B it is. All right, here we go. Find all the times in the interval when the particle changes direction. Ooh, changes direction. Ooh, think about velocity. If velocity is 0, it comes to a stop. If velocity is positive, it was moving to the right. If velocity is negative, it's moving to the left. Okay, let the calculator do all that, right? So I'm going to go and say, listen, calculator, show me the velocity. Okay, so here, and I think, did they tell us, from 0 to 3? Okay, so hang on, let me not mess around too much. Let's make this go from 0 to 3. Okay, calculator, do tell. Oh, look at that action. Okay, now watch. All of these are plotted. Let me demonstrate something in case you don't understand what I'm saying. Do you see this point right here? This is x comma y. This is the x. This is the velocity, 2.8. That's a positive velocity. Then I'm going to work my way over here, and I'm eventually going to get to 0, right? Velocity. Matter of fact, hang on, second calc. Let's let the calculator find that. So I've got more math backing up my conclusions. Oh, I can't see what I'm doing. Okay. Let's go past it somewhere. Somewhere in there. Okay, hang on. It's going to find it for me. There it is. See, at the x value of 2.7, velocity is 0. And then do you see how all of a sudden over here, the velocities become negative, don't they? Oops, I just hopped off the graph, didn't I? Sad. There it is. Okay, velocities become negative. So watch how they're stating this. Okay. See how you're proving to them you understood that that's where the velocity is 0, and then it changes from positive to negative. Or you can use interval notations. You can say, from 0 to 2.707468, all right, it was moving, to the right, because those were positive, and then from 2.707468 to 3, I'm going to include 3. Oh, I should include 0 too, huh? Because actually at 0, it's a positive velocity. So notice, and then I would say moving to the left, okay? Something of that sort, all right, to get those 2 points. Notice they do want you to not just guess. I mean, anyone can guess. It's moving to the left and then moving to the right. No, I feel like it's moving to the right and then moving to the left. Don't just guess. You got to give them some math background and knowledge, proving to them you actually know what you're doing. You're not guessing, okay? All right, and then one for some kind of a justification, all right? Okay, any questions on B? You guys are looking like you're, if you feel, if you want to get up and do some jumping jacks, by all means, you do that. Do whatever it takes to get the blood flowing. I'm going to move on to C though, okay? But I won't be offended if you want to get up and do some jumping jacks while you're listening. I get it. Find the position of the particle. Oh, position. Okay. Oops. That's like x of t. But we wanted it times 0. Okay, all right, x of 0. All right, what do you do with position? Well, I guess I could make it more specific now. We need to have, quote unquote, a start. We need to start somewhere. Where do we start? Oh, look at that. At x equals 2, the time was 4. That's a start, what I call, quote unquote, start. Okay, so when position's 2 at time, look how I did that, 4. All right, I'm going to accumulate the change of the position from 4 to 0, because that's what I'm trying to do here. I'm trying to reach 0. If this amount is positive, it'll add it to 4. I'm sorry, it'll add it to 2. If this amount is negative, it'll add it to 2. It will take care of it for you. You don't have to worry. Calculus is on your side, okay? So what are we going to anti-derive? Well, remember, if you have velocity like we have here, the only way to get position is to anti-derive velocity. And that's what I'm doing. I'm going to anti-derive the velocity from 4 to 0, and figure out what amount of displacement happened there. And then I got to tack it on to when the clock started, which was in 4 seconds. It started at 2. Okay. Does that make sense? And you let the calculator do all that. You don't mess around. Watch. Here, we're going to let it do it. Ready? 2. I'm going to go to my home screen. 2 plus, and I'm going to let it do all the work. Oop, number 9. All right. I'm running it from 4 to 0. I'm accumulating all that wonderful velocity, which for me now is in y2. Okay, with respect to, come on, there it is. All right, and that is the position. All right, so let me go back to this. Let's go down and see how they, just a second. Okay, let's see how they graded it here. All right, there it is. Did I get the negative 3.81? Yeah, okay. I want to make sure I didn't type a 5 and a 4 or something weird. Okay, and so notice you get 3 points for this, okay? Let me back it up, that's a bit much. 1 for the integral, that means you understood you had to anti-derive velocity. You understood that. 1 for going, oh, that's right, I gotta tack on that initial condition, okay? And then 1, of course, for the final answer. Is that all right? Any questions on that one? No? Okay, last one, you ready? Uh-oh, some of your eyes are just starting to fall. You got this, hang in there. Okay, letter D. Okay, find the total distance. Okay, if I walk 3 paces to the right and I turn around and walk 2 paces to the left,
Oh my
that
god.
is a positive 3 for velocity and a negative 2 for velocity, or depending on how you're looking at it, displacement, right? Positive 3 for displacement, I guess is what I should say, because I don't know my rate. Sorry about that. But you're walking 3 paces to the right, 2 paces left. I want to know that I walked a total of 5 paces. Okay? I just don't want to accumulate the 3 and the negative 2 and call it a 1 pace. No, I put a lot of effort in my paces. Okay? So what you want to do is to find the total distance. You take that velocity, and instead of just the integral, because that would give you the displacement, the overall change of displacement, we don't want that. We want all negative velocities to turn positive, right? And all positive velocities to stay positive, and we just want to accumulate all of them, all right? And so we're going to do that from 0 to 3, just like that. Now I'm going to show you on the calculator. Oh, let me show you the scoring guideline. I'll show you on the calculator how to do that. 1 for the integral and 1 for the answer, okay? So on the calculator, here's what you would do. You would start with your math button and go to function integrate. We would run it from, oh, I already forgot. Why did I just forget? 0 to 3, okay. 0 to 3. Okay. And then this calculator can do absolute value. It's under math and then num at the top. You have to cursor over to num. There is absolute value. And then that's when you go grab the vars feature, right? Which hopefully we all know how to do that by now. All right. And then with respect to x. And it will turn all of those negative velocities into positive ones. It'll accumulate them all. And there you go. That's your total distance. Okay. Here's the statistics. For question number 2, the average was 3 points out of 9. Okay, so that's for your information. All right. Okay, we still have about 15 minutes. I'm now going to send you one more great response. It's coming out of the 2015 here.